Hello, I'm Mo Kiali, graduate student at the University of Washington. I want to talk to you today about my paper, Quasi-Stable Colorings for Graph Compression, a joint work with my advisor, Dan Suchu. So, to start, let's talk about color refinement, also known as one-dimensional Weisweiler-Lehmann. If you've heard of vertex coloring, just that's distinct from proper vertex coloring, chromatic number, just keep that in mind. But otherwise, this is a method of assigning colors to nodes in a graph in the following way. So you start by giving every node the same color, and you iteratively refine those colors by looking at the neighbors of the node. So here, initially, all the nodes get blue, and then in the first round of the algorithm, we assign colors to nodes depending on their neighbors. So the light blue nodes are those nodes which have one purple neighbor and one magenta neighbor, and two blue neighbors. And we continue this until we reach a fixed point, right? Until the colors do not change after each round, and we call this a stable coloring. Okay? If you'll permit me some formalism, let's define a stable coloring, P, right? This is the colors make a partition, so we call it P. We call it stable if for any two colors I and j, every two nodes in the first color have the same number of neighbors n into the color j as each other. So two nodes in blue will always have the same number of red neighbors, for example, right? Now, why is this interesting? Well, this algorithm, kind of a folklore algorithm, was identified as a very good heuristic for graph isomorphism testing, right? So if two graphs have the same coloring, they are almost certainly isomorphic. And given that this was an open, exciting problem, there was a lot of attention given to color refinement for this problem. However, much more recently, there's been this emerging application of dimensionality reduction, right? In particular, using color refinement as a way to capture the structure, the inherent structure of a graph, compress it, and generate a lifted graph, right? So here, after coloring the graph with a stable coloring, we make one node, we collapse all the colors into supernodes, right? And draw an edge between them if those colors are connected in the ground graph. We call this a lifted graph or a quotient graph. So let's apply this this emerging application for dimensionality reduction. Here I have a real life graph. This is a social network of a karate club. This karate club, each node here is a person, and the link between two people is if they know each other, if they have a friendship, right? So this is a graph of a club with 34 people and 78 friendships. Now, if I apply color refinement to compress this, I run into a problem immediately, which is the number of colors required is almost the same as the number of nodes. In particular, I need 27 colors to color these 34 people. And this is a problem because my lifted graph will have 27 nodes, so my compression ratio is really not that good. But you might say, well, we got unlucky, right? That particular graph doesn't work well, but it might work for other ones. And the issue is, this is not the case. So if I try with larger graph, flights, which is a global airports graph, or DBLP, a scholarship citation graph, the compression ratio, right, only gets worse and worse and worse. And so this is a problem, right? In fact, theory results show that this will systematically be a problem. If you have a random graph with n vertices, right, it will almost certainly require the probability that it requires n colors to compress it is very high. Okay, so to allow these colorings to be used for real-life colorings, we introduce quasi-stable coloring, right? So this is a generalization in which we loosen the requirements such that two nodes in one color do not have to have the same number of neighbors, just the number of neighbors that differs by some constant, right? And we call that constant Q. So we say quasi-stable or Q-stable coloring. And if we look back at our karate club graph that was so difficult to color with the stable coloring, right? Our approximate version is able to use 6 colors only to compress this graph if we allow this error of 3 edges. And in fact, this club has 2 leaders, right? 2 teachers. And we find that our coloring has managed to capture that structure. Those are nodes 1 and 34 with the red color. And you can see the students, mostly in green, get their own color. And in fact, this ability to remain robust to noise that's present in graphs scales very well. So here I have a random graph I've made with 1,000 nodes, and I've constructed it artificially to have to be able to be colored with only 100 nodes. And you can see if I just add a small amount of random edges, this graph has 10,000 edges, so I'm adding less than 1%. What you're seeing here is very quickly the stable coloring degenerates into that worst case scenario shown in the green line, right? Green line means as many colors as nodes. Whereas our quasi-stable coloring with just a budget of 4 edges is able to stay robust and not break down. The catch, however, is the algorithm is more difficult now because the stable coloring has a nice property that any refinement order, all refinement orders are equivalent because it doesn't matter which color you choose to refine first. This is not the case for quasi-stable colorings. The order in which you partition makes a big difference to the quality of the coloring. This is because there's many distinct options to color for any fixed value of Q. So we develop an algorithm, you can see it in the paper. The exciting part, however, now is applications. So we find that for 3 classes of problems, maximum flow, linear optimization between the centrality, there's the very attractive property of the result of running the algorithm on the full graph is approximately equal to running the algorithm directly on the compressed graph without having to decompress it. This means this can be an effective approximation. So we look at about 20 types of real-life graphs, number of nodes ranging from a few thousand to the millions, mostly real data sets, from benchmarks for centrality, maximum flow, and linear optimization. We find that our compression quality is very good. We have an excellent trade-off, meaning depending on the value of Q you set, you can get compression ratios from 10x to easily 1,000 or more, and kind of trade off how much compression and space you want to use. The exciting part, however, is this compression allows for end-to-end speedups. So if we measure the time it takes to compress the graph, run the algorithm on the compressed graph, and return that result, we find that on average we have speedups of, if you want a speedup of 100x, we have a geometric error of 1.2x, right? So if you have a budget error of approximately 20% relative, we can give you 100x speedup. And we find this, to require a small number of colors, no more than 35 or 100, 150 for these applications. Excellent. We also compare with approximation algorithms designed specifically for 2 of these algorithms between the centrality and linear optimization, and we find that our more general approach, which can approximate many classes of problems, actually beats the speed of dedicated approximations if you fix a particular approximation budget. So to recap, I told you today about quasi-stable colorings, our generalization of stable colorings so that they can be robust to noise and used on real-life data. I've shown you 3 applications for this. I invite you to read our paper, find the reference implementation on GitHub, and there is a package with documentation and tutorials available for the Julia language. So please do install it. That's all. Take care.